We have a chemical reaction. Okay, that chemical reaction we'll call the system. Okay, everything around it. Okay, everything around it, we'll call it the surroundings. Thank you. Okay, this includes the test tube. This includes the beaker. Okay, so we have system and surroundings and system. There's two ways these two can interact with one another. Okay, one way is that they can do work on each other. Okay, so work is a type of energy. Okay, work is a type of energy. There's many different types of energy. In fact, if you look at the definition of energy, it's the capacity to do work. Okay, work we'll call lowercase w. And look at all this types of energy that is available for us that can do work. Okay, this is energy that can be harnessed. Okay, from a biology perspective, maybe it's the energy to contract a muscle, or for an E. coli cell to move. Okay, anything that requires something that's done that requires energy. Okay, it does work. Okay, so the system can do work on the surroundings can do work on the system. So we came up with this skit where we said, it was Gerardo, right? So if I'm the system and I do work on the surroundings, okay, work done by system on surroundings. Okay, what is the sign of the system? Is it positive or negative? Do you remember this? Okay, it's going to be negative. What will be the sign of the surroundings? Okay, it's going to be the exact same value but positive. Okay. What about work done by the surroundings on the system? Work done by surroundings. What are the surroundings? Okay, everything. The glassware, the universe, you, okay, me. Okay, work done by the surroundings. If it's done by the surroundings, that value, that number is negative, and the system gets positive. Okay, so there's work energy, and then there's heat. Okay, heat is Q. Okay, so heat is something that dissipates. Heat just goes away, or you add it to the system. Okay, so if system releases heat to the surroundings, okay, heat Q to the surroundings, okay, what is the sign of the system? It releases heat. Okay, so it's going to be a minus sign, and the surroundings will be positive. Okay, so what type of reaction is this where the system releases heat upon a chemical reaction? It releases heat to the outside. This is called an exothermic reaction. Okay. Right. This heat Q can be taken in by the reaction. It can be taken in by the system. All right. So this is where the system maybe absorbs heat or takes in heat from the surroundings. Okay, from the surroundings. Okay, what is the sign of the system? Okay, what is the sign of the surroundings? Okay, so the surroundings give heat. Okay, if they give heat, then or it releases heat. If something releases heat, if I release something, okay, I become negative, and someone else takes it, they become positive. With regards to the system, this is an endothermic reaction. Right, so an endothermic reaction usually we say involves or requires energy in the form of heat, or we'll just say it requires energy. Requires energy. And then an exothermic reaction releases energy. So this is how the system and the surroundings communicate with one another. Now, units, okay, and the actual thermodynamic variable, the thermodynamic term is called enthalpy. Okay, enthalpy. Okay, there's three major thermodynamic parameters. Okay, there's a thermodynamics course offered here at Methodist. It's like 4,000 level. It's like one of the highest chemistry courses. It's called thermodynamics. So chemistry majors are required to take it. Okay, so I think you'll be taking that. So there's three parameters. We're only going to focus on one. Okay, I'll only teach you one, and that's called enthalpy. And more specifically, it's called change in enthalpy. Okay, so it's delta H. Okay, this delta means change in. Okay, and we're talking about change in heat flow. Okay, either from reactants to products or products to reactants. Change in heat flow. This is delta H. Okay. There's also delta HF and standard state. This is called naught. Okay, so this is naught, delta H naught. Naught. Okay, delta H naught. This is called formation. Okay, you'll see this in your textbook. This is called standard enthalpy of formation. Okay, the amount of energy required to form 1 mole of a substance in standard state conditions. Okay, standard enthalpy of formation, which is something you see in the back of your textbook, or you can look it up online. And just a brief definition, energy required, or some cases released, energy required or released to make 1 mole of a substance. Okay, energy required or released to make 1 mole of a substance under standard state conditions. Under standard state conditions. All right, so what are standard state conditions? Typically they are 1 atmosphere, 25 degrees C. Okay, if you're dealing with aqueous solutions, it's 1 molar. So very specific set of conditions, and they'll give you the enthalpy of formation. All right, so this and this are not the same. Okay, this is something that, is not the same as this. This is something we calculate. This is something you see in your homework. This is something you'll see on the test or the quiz. And this is something you'll look up in the back of a textbook. Okay, you use a lookup table. You look up these values. If you have a textbook or the PDF book or the internet, you look up these values. So there's 3 thermodynamic parameters. I'm only going to focus on one, and that's delta H, which is enthalpy. Enthalpy, a change in heat flow. Okay. So this is an important part of this lecture, an important theme. Okay, delta H. Okay, in Chem 2, they'll teach you delta S, delta G, okay, a couple of other terms, but right now we're just focusing on delta H. All right, I'm going to move on to page 2 now. So delta H, standard enthalpy of formation. If you're not understanding this too well, or maybe you're confused, just realize you can look this up in your textbook. These are values that are there that you look up. This is something that you calculate. This is under any conditions, and this is under a very specified set of conditions, and since they're so specific, you can look up these values. Another thing I want to tell you guys is the units. Okay, the units here, okay, we want to put the right units, and the units are going to be joules or joules over mole. Units for enthalpy or units for energy. Okay, it's going to be joules. Okay, or joules per mole. Can also be kilojoules per mole. Okay, sometimes we see calorie. Maybe you may have heard of that. Okay, but in this class, I'm going to go with joules or joules per mole. Okay, I'll give you the conversion if have calorie to joules, joules to calorie. All right, so these are the units that we want to accustom ourselves to speaking, okay, when we're talking about energy. So now let's go on to page 2. All right, so you can look at this definition here. Heat is the transfer of thermal energy between two bodies that are at different temperature. Okay, once again, I just want to tell you that it's given the term Q, lowercase q. And usually heat dissipates. It cannot be harnessed. Work can be done. It can work, radiant energy, chemical energy, ATP, okay, gravitational energy, solar energy, kinetic energy, all of these types of energies does work. Okay, heat just dissipates. Okay, really cannot be captured or harnessed. Okay, so it cannot really do work. It just, comes and goes. So there's different types of systems here. This would be what's called an open system. Okay, so in the open system, remember the surroundings are everything around it. Okay, the surroundings also include the flask, the test tube, the beaker. Okay, that is also the surroundings. So in an open system, work can be done by the surroundings on the system. Work can be done by the system on the surroundings. Heat can be interchanged between one or the other. Okay. Now, in a closed system, okay, they put a cork. Okay. In a closed system, the only thing that can be exchanged between the system and surroundings is heat. And then finally, in an isolated system, okay, nothing can be exchanged. No heat and no mass, no nothing. Okay, nothing can be exchanged. Okay. Have you heard of this term called hermetically sealed? Hermetically sealed. That means this has a constant temperature and a constant pressure. Okay, this is an example of an isolated system. Okay, a hermetically sealed. Means the pressure inside here stays the same, the temperature inside here stays the same. so on and so forth. All right? So you have isolated system, closed system, and then we have an open system. All right. And now let's go to page 3 here of our notes. All right, I want to tell you guys about exothermic and endothermic reactions. Okay, you see this reaction here, 2H2 plus oxygen goes to water. Okay, hydrogen is a gas, oxygen is a gas, water is a liquid. Those are the 3 states. But what else is a product here? What else is a product besides liquid water? Energy. Okay, energy. Okay, energy. So a reaction that uses energy or creates energy or liberates energy as a product is called an exothermic reaction. So where will energy be in an exothermic reaction? The reactant side or the product side? It will be in the product side. Okay, furthermore, this enthalpy, the change in heat flow, which is, products minus reactants, the change in heat flow for this, it will be negative. Okay, delta H, this enthalpy, change in enthalpy, will be negative for an exothermic reaction. Okay, this is something we must know. Okay, if you have a reaction that's exothermic, what will delta H, the change in enthalpy, be? Okay, it will be a negative value, negative. Okay, remember, anytime you see delta or change in, it's final minus initial. Okay, products minus reactants. All right, let's look at this reaction with me. Okay, here we have water as a solid going to water as a liquid. And what else do we see here on the reactant side? Okay, we see energy. So this requires an input, okay, some sort of oomph, some sort of push to make solid water reactant go to liquid water product. Okay, so here energy is on the reactant side. This is called an endothermic reaction. Okay, and where will energy be in an endothermic reaction? Will it be on the product side or the reactant side? Okay, it will be in the reactant side. Okay, and this delta H, the change in enthalpy, okay, products minus reactants, change in enthalpy, final minus initial, products minus reactants, this delta H will be positive. Okay, positive. Okay, what will the reverse reaction be? What happens if I flip this reaction? What will it be? This will be endothermic. Okay, so if you flip the reaction, okay, now energy is on the reactant side, so this becomes endothermic. What happens if you flip this reaction? Liquid water going to solid water. Okay, it's going to release heat, release energy. So if you flip the reaction, this becomes exothermic. So key point here is that if you flip a reaction, you flip the sign of delta H from positive to negative or negative to positive. So here you can see the difference between an exothermic and an endothermic reaction. In an exothermic reaction, energy is going out, and in an endothermic reaction, energy is going in. Okay. All right, I will not test you on this, but this delta H, okay, this delta H is called a state function. Okay, this term in thermodynamics called enthalpy, or change in enthalpy, is a state function. So just very briefly, I'll tell you what a state function is. Okay, you'll see this a lot in the thermodynamics course, but let's take a reaction here. Okay, a hypothetical reaction of A goes to B. Okay, A goes to B. Okay, so A goes to B, and the delta H is, I do not know. I'm just throwing out some numbers here. Minus 100 joules. Okay, just random number. Okay, it's minus 100 joules. So that minus sign tells us that it's exothermic. Okay, so now what is the state function? Okay, what is the state function? So A goes to B. A is the reactant, B is the product. Okay, A is the reactant, B is the product. So this can go straight, one shot, single step, A to B, done. Or it can go from A to C, some intermediate C to B. Okay, one step, okay, or one intermediate. Or it can go from A to X, and then X goes to Y, and then Y goes to Z, and then the molecule, the chemical becomes Q, it changes, and then it finally goes to B. Okay? So whether it's A to B, or AC to B, or AX, Y, Z, Q to B, it will always be minus 100 joules. So basically, it doesn't matter how, or the mechanism by which the reactant goes to product. It does not matter the mechanism by which A goes to B. Okay, whether it's 100 steps or whether it's one shot, single step, it doesn't matter. Okay, this delta H will always be whatever number. Enthalpy will always be minus 100 joules. Okay? Kind of like if you're scaling a mountain. You're scaling a mountain. Okay, how will you scale a mountain? Or is there just one path? Okay, how many paths are there? Okay, there's many different paths, okay, to scale a mountain. You go to the one that the least terrain, most terrain, okay? So either way, what's your final destination? The top, very good, okay? Okay, so no matter what way or path you go, you'll always reach to the same state, same destination. No matter what path you go, you will always go to the same state, same product, and that value will always be whatever it is. Okay, so that is an example of a state function. Okay, enthalpy is a state function. This value will always remain whatever it is, minus 100, no matter how reactants go to products. All right, so sometimes we have the change in energy of the system as delta U, okay? So change in internal energy of the system. Okay. So the internal energy of the system has inputs from Q and W. Okay, internal energy of the system. Okay, so the system will, take in heat or release heat. Work will be done by the system, or work will be done on the system. Okay, so delta U is internal energy of the system. Okay, when we're talking about gas, we're talking about pressure volume work. Okay. Right, so this is a review from what we did earlier in the class. Really quickly here. Okay, work done by the system on the surroundings. By the system, so the sign of the system will be negative. Work done on the system by the surroundings on the system. On the system. Okay, positive for the system. Heat absorbed, absorbed by the system. Okay, by your reaction, by the system. Okay, what sign will that be? Positive. What do we call this reaction? Should be a review. Endothermic. Good. Heat absorbed by the surroundings. If it's absorbed by the surroundings, who's releasing the heat? The system. Okay, so what's the sign for the system? Negative. And quick review, what is this type of reaction called? Exothermic. Okay, exothermic. All right, let's talk about gases now. Okay, remember gases? Okay, you breathe in, you exhale out. Okay, you're exhaling gases. Okay, you're exhaling CO2, you're taking in oxygen. So gases also have this work and work situation. We call it pressure volume work. Okay, let's go to page 5 now. All right, so here you have a bunch of gas molecules. Okay, what has happened to this gas? What has happened from initial to final? Okay, it has gone up. It has expanded. Okay, so when this gas expands, okay, what has happened to the volume? It increases, okay, from here to here, okay? From here to here. So this increase in volume, or the change in volume, implies that the gas has done pressure volume work. So if this gas is the system and everything to the outside is the surroundings. Okay. And the gas is the system and the surroundings are everything else. What is the sign for the gas, the system, and what is the sign for the surroundings? The gas is expanding. So what's the sign for the system? You only have two guesses, positive or negative. Okay, it will be negative, okay, because the gas is doing work. Who is it doing work against? The surroundings, okay? So what is the sign of the surroundings? Positive, okay? So here we say the gas is doing pressure volume work. Doing work, and it's doing work, so gas expansion means pressure volume work, okay? Okay, P delta V, pressure volume work. Okay. So what would be the sign for the energy for the system here, the gas, positive or negative? Okay, for a gas expansion, the gas would be negative. Okay, what would the surroundings be? Okay, the universe or the surroundings would be positive. Okay, so pressure volume work for gases. See, there's only two things you can change for a gas. You can change its pressure, you can change its volume. All right, so that is for the case of gases. Okay, let's do this problem together, and then we'll do some enthalpy problems. All right, a gas expands. Okay, it expands. Okay, and does pressure volume work on the surroundings equal to 279 joules? Okay, does pressure volume work on the surroundings equal to 279 joules? At the same time, it absorbs. Okay, let's put this in green ink. Absorbs 216 joules of heat. Okay, so the work it does is 279 joules. The heat, which is lowercase q, is 216 joules from the surroundings. What is the change in the energy of the system? Okay, so one of our equations a couple of pages ago was the change in the internal energy of the system. Okay, the gas. Okay, it will give or take in heat, or it will do work or have work done on itself, okay, by the surroundings. All right, what is the sign for Q here for this gas? Positive or negative? It absorbs. It's going to be positive, good. And it does pressure volume work on the surroundings equal to 279 joules. It does work on the surroundings, so it's going to be negative. Okay, so the change in the internal energy of this gas will be 216 minus 279. And what is that on our calculator? Minus 63. Joules. So is the gas doing work against the surroundings? Yes. Okay, the gas is doing work against the surroundings. Okay, this minus sign tells us the gas is doing work. Pressure volume work. All right. Let's go to page 6 now. Kind of the same thing here. Enthalpy is heat flow. Maybe I forgot to mention this, but this enthalpy is usually done at constant pressure. Okay, and when I think of enthalpy, I want you to think of heat flow. Okay, final minus initial, products minus reactants. Okay, so there's an equation that we'll utilize here, and it's the delta H. And it's going to be the sum of the delta H products, okay, minus the sum of the delta H reactants. Okay, you take the sum of the products minus the sum of the reactants, and sometimes you have to multiply it by the coefficient, the stoichiometric coefficient. We'll do a practice problem involving this. And this also holds true for standard state. Okay, this is standard state. Okay, 1 atm, 25 degrees C. Okay, same thing. Okay, we'll do some practice problems involving this. Okay, this m means stoichiometric coefficient. Products minus reactants. Okay, products minus reactants. Change in enthalpy. Okay, we don't measure just H. Okay, that's pointless. We measure the change. Okay, is the heat going this way more, or is the heat going to that way more. So let's look at this reaction together here, okay? CH4 plus 2 O2 gas goes to CO2 and 2 water. This is called a combustion reaction. Okay, is this reaction exothermic or endothermic? Okay, the minus sign should tell you it's exothermic. So what else is a product here? Okay, energy. The minus sign tells you it's exothermic, and it tells you what else is the product? Energy. So this equation is balanced, and then you have all these different relationships. Okay, for every 1 mole of CH4, it's minus 890.4. For every 2 moles, it's minus 890.4 for every 1 mole. Okay, these are from the balanced chemical equation. Right, let's look at this reaction here. Okay, look at this reaction with me. CH4 plus 2O2 plus goes to CO2 plus 2H2O gas. Is this exothermic or endothermic? Exothermic. What else is the product here? Energy. Okay, so what's the difference between this reaction and this reaction here? Okay, very good, Husong. Okay, the state of H2O. Okay. So you see in this reaction, the state of H2O is a liquid. I'm not getting them to line up. Okay, but in this reaction, what is the state of H2O? Gas. Okay, gas. Everything is the same. Okay, this one gives you a gas in water. What will this one give you? Liquid. Okay, so that's why their values are the same, different. That's why their values are different. Okay, they're both exothermic. Okay, they both have negative enthalpies, but one gives you gas water, the other gives you liquid water. Okay, what's the point here? Okay, the take-home point is that states matter. Okay, states matter. Okay, whether it's a solid, it will give you a different delta H, whether it's a liquid, whether it's a gas, whether it's aqueous. Okay, all of these will have different delta H values. Okay, everything could be the same, but the delta H values could be different if you're talking about solid H2O versus liquid H2O versus gas H2O. Okay. The delta H will vary. When you look it up in the back of your book, the values are going to be different, so the states matter. All right, couple of points here. We already talked about this before. If you take a reaction and you reverse it, what do you do with the sign? Okay, if you reverse a reaction, what will you do with the delta H? You what? Flip it. Okay, you flip the delta H. Okay, flip the delta H. What was positive becomes negative. What's negative becomes positive. What happens if you take a reaction and multiply it by some number? Okay, if I take this reaction and multiply it by 2 or 3 or 4 or 5, okay, what happens to the delta H? Okay, you will multiply it by that same number. So you multiply a reaction by n. Okay, the delta H gets multiplied by that corresponding number n. So those are two rules that I'd like for you to know. Okay, flip a reaction. What happens to delta H? The sign changes from positive to negative or negative to positive. What happens if I take a reaction and multiply it by 2? Then you have to multiply what by 2? You have to multiply delta H by 2. That's correct, David. Okay, what happens if I multiply this reaction by 3? Okay, what will the delta H get multiplied by? 3. What happens if I multiply this reaction by 1/2? Okay, what will you multiply delta H by? 1/2. Okay, 1/2. Okay. So for whatever reason, a lot of students miss this. Okay, whatever you do, when you multiply a reaction, you multiply the delta H by that same reaction. Okay, please do that. Obviously, if you flip a reaction, you flip the sign. Okay, so those are two rules that I'd like for you guys to know. All right, let's do a problem here. All right, calculate the heat evolved when 266 grams of white phosphorus P4 burns in air according to this equation. Okay, so the equation is balanced. So we have 266 grams of P4. Okay, let's go ahead and convert that to moles. So 1 mole of P4 contains how many grams of P4? Okay, what is the molecular weight of phosphorus? Okay, heat evolved. So what do you expect the number will be? Positive or negative? Okay, you got it. Negative. Okay. You can see the negative here. This is an exothermic reaction. Releases heat. So what else is a product? If it's an exothermic reaction, energy is a product. So 266 grams of white phosphorus, we'll convert that to moles. P4 is 30.973. Okay, times 4. What's 30.973 times 4? 123.89. Okay. Okay, and then for every, now we'll use this relationship now. Now we know this. For every 1 mole of P4, there is minus 3,013 kilojoules. Okay, so per mole of P4, we will get, so P4 reacting with this will give us per mole of P4 266 times minus 3,013. Okay, divided by 123.89, about minus 6,469 kilojoules. Okay, this is our answer. So this is coming from our enthalpy. All right. So calorimetry is our next topic. I think you'll have a calorimetry lab in a couple of weeks, so you guys can look forward to that. We have specific heat, and then we have heat capacity. So I'll just read this out. You can just read it along with me. All right, so read with me here. Specific heat is the amount of heat required to raise 1 gram of a substance by 1 degree C. Okay, the units are joules over grams degree C. Okay, amount of temperature, or amount of heat required to raise 1 gram of a substance by 1 degree C. Okay, this is the specific heat. Okay, so it's a constant. You can look at, there's a specific heat. Do you know which substance has the highest specific heat? Okay, water. Okay, strangely enough, water has one of the highest specific heats. All right, read this along with me for the heat capacity. All right, heat capacity, amount of heat required to raise the temperature of a substance by 1 degree C. Okay, 1 degree C. So this also is a constant, but it's joules over degree C. Okay, heat capacity. Okay, heat capacity, C is a constant. Specific heat, specific for 1 gram is also a constant. What has one of the highest heat capacities known to man, known to mankind? Water. One of the highest specific heats, water. Okay, so one of the strange properties of water. The equations that will utilize these constants is Q equals C delta T for heat capacity, and then Q equals MS delta T for specific heat. I'll give you those equations on the exam. Okay. Okay, what is delta T here? Okay, change in temperature. Okay, change in temperature. Time is going to be in this class lowercase t, but we don't study time here, or how fast. That's lowercase t here. Delta t is temperature. So this delta t is final temperature minus initial temperature. This is change in temperature. Okay, what is M here? Mass. Okay, what is S for this equation? Specific heat. What is C in this equation? Heat capacity. And finally, what is Q in this equation? The main point of this chapter. Lowercase q is heat. Okay? So these are the two equations we will use. Alright, so we got about another 15 or so minutes. Let's do some problems here. So an iron bar of mass 869 grams cools. Okay, it cools from 94 degrees to 5 degrees C. Calculate the heat released in kilojoules by the metal. The specific heat S of iron is 0.444 joules over grams degrees C. Okay, so we have an iron bar. Okay, 869 grams. Okay. It cools. Okay, so this is initially at 94 degrees. Okay, and it's giving off heat. Okay? It's giving off heat. Where's the heat being released to? Surrounding. So would this be an exothermic or an endothermic phenomenon? Cooling. This would be exothermic. So what would the sign of Q be? Positive or negative? It would be negative. Okay, Q would be negative. Okay, so we have our specific heat here as 0.444 joules over grams degrees C. Alright, I'll give you this equation. I'll give you the specific heat constant. You just have to plug and play. Q equals ms delta T. Okay, the mass of this piece of iron is 869 grams. Okay, the specific heat given to us is 0.444 joules over grams degrees C. And then final minus initial. Okay, what's our final temperature? What's our initial temperature? 94. Okay. So the grams cancel, the degree C cancel. So 5 minus 94, 89, minus 89, times 0.444 times 869, getting about minus 34,339 joules. Okay? That's how much heat is released to the surroundings. You can divide it by 1,000 and say minus 34.3 kilojoules. So one and the same. Okay, so this is released to the surroundings. The negative sign means it's released to the surroundings, this heat Q. All right, we're almost finished with this chapter. So why don't we do one more problem and then we'll call it a day. We'll wrap up this chapter on Thursday and then start chapter 7. Okay, so we got one more problem to do. All right, you guys will have a lab doing this sort of stuff, enthalpy of a reaction, so you can look forward to that. I mentioned a little bit about standard enthalpy of formation. Standard enthalpy of formation. Okay, this is the textbook, the old textbook, but if you're using the PDF textbook, it's a different chapter, different section. And then, okay, this is standard state. This is enthalpy of formation. Formation is 1 mole. Okay, we look up these values in the book. Okay, look up tables. All right, let's do this problem here, and then we will wrap up the class here. All right, so this problem involves a type of law called Hess's law. Okay, so I'll read out Hess's law before we do this problem. Okay, when reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. Okay, so in other words, sum of the products minus sum of the reactants. Okay. Actually, this is Hess's law is more of this practice problem that we'll probably do on Thursday. But what I want you guys to do is do this equation here. All right, so let's go to this practice problem. All right, benzene burns in air to produce carbon dioxide and liquid water. Okay, calculate the heat released in kilojoules per gram of the compound reacting with oxygen. The standard enthalpy of formation of benzene is is 49.04 kilojoules per mole. Okay. So calculate the heat released. So what do you think the sign will be, positive or negative? Okay, it's going to be negative. All right, first thing we want to do here is our equation. This is the breakdown of benzene C6H6. Okay, the first thing we want to do is balance this equation. All right, so let's balance this. Okay, so we got 6 carbons and then 3 hydrogens here. That makes it 6. And then 12 plus 3 is 15. So I'm going to put 15 halves here. Okay, that should balance it. I'm going to multiply both sides of this chemical equation by 2. And this will give me 2C6H6 plus 15 O2 so this should be balanced. Yep, balanced, right? So we will utilize this equation up here. Okay, sum of the products minus sum of the reactants. Okay, this will give us the delta H of the reaction in standard state conditions. Okay, why is it standard state? Okay, because of this little not symbol. It tells us it was in standard state conditions. All right, sum of the products minus sum of the reactants. Okay, so for this reaction under standard state conditions, we'll take the sum of the products minus the sum of the reactants. Okay, we got our balanced equation. So what is our first product here? Okay, we'll do CO2, and it's CO2 gas. Remember, states matter. So states matter. So this is a gas, this is a liquid, this is a gas, and oxygen is a gas. Okay, so we'll do CO2 gas. If we go to page 12 here, CO2 gas is, it's hard to see, so on the exam, definitely I'll give you one that's more clear. But if I squint and see CO2 gas, it's going to be minus 393.5. Okay, so these are the delta H standard enthalpy of formation values. Okay, that we use the lookup table. So we look up CO2 gas, minus 393.5. That's for 1 mole. This is for 1 mole. How many moles do we have? 12. So we got to multiply this by 12. Kilojoules per mole. Okay, what's our next product here? Okay, we got our CO2. What's our next product? H2O. H2O liquid. So that's H2O liquid here. Okay, I know it's hard to see, but I'll give you one that you can see on the exam. This is minus 285.8. That's for 1 mole. How many moles do we have? 6. Okay. So 6 times minus 285.8 kilojoules per mole. Okay, so then minus, here's our minus. Okay, I want you to put a big bracket. Okay, a big bracket. Okay, now we got our products. Let's do the reactants. What is one of our reactants? Benzene. So this is for 1 mole of benzene. How many moles of benzene do we have? 2, so it's going to be 2 times 49.04 kilojoules per mole. Plus oxygen, O2 gas. Okay, O2 gas should be 0. It's the base element. Base element is 0. Even if you don't know it's the base element, you'll see that oxygen gas is 0. Okay? You can look it up. Okay, 0. Okay, O2. I know it's hard to see, but on the exam you'll have this, and you'll have it so you can read the numbers. Okay. All right, so you just look up these delta H standard enthalpy of formation values. You look them up into the table. Look up these values in the table, and you plug it into this equation. Okay, so oxygen is 0, and that's for 1 mole. How many moles do we have? 15. Okay, make sure you choose the right state. Okay, gas, liquid, make sure you choose the right state on the exam. All right, so now it's just algebra now. Okay, this is where students make some mistakes. One mistake is that this minus distributes. Okay, so products minus reactants. So this minus, like a train, it distributes. So what is 2 times minus 49.04? 98.08. So it's going to be minus 98.08 kilojoules per mole. Okay, what's 6 times minus 285.8? Okay, minus 1714.8. That's minus. Okay, what's 12 times minus 393.5? Minus 4722. Okay, so what is this on your calculator? Minus 4722 minus 1714.8. Okay, minus 98.08. Okay, getting minus 6,535 kilojoules per mole. Okay, minus 6,535 kilojoules per mole. Right, so on the exam, this would be the answer that would suffice. This would be the correct answer. But if you look at this problem a little bit more carefully, this is the heat released in kilojoules per gram, okay, per gram of the benzene. So we have to do an additional step to calculate this per gram. Okay, so on the exam you don't have to do that, but to answer this specific problem, to answer this specific problem, you need to do it per gram. Okay. So per gram of benzene, we'll take this, minus 6,535 kilojoules per mole. Okay, and 1 mole of benzene is how many grams of benzene? Okay, 12.01 times 6 plus 1.01 times 6, 78.12. Benzene. Okay, the moles cancel. We'll take this, and we'll take this number, which is our answer per mole. We'll divide it by the molecular weight to get it per gram of benzene. And what do we do when we get that? Okay, minus 83.7 kilojoules per gram of benzene. Okay, so this should be the answer. All right. Okay, on the exam you just have to stop here. Okay, you can just end it there. All right. All right. So